So moving right along with chapter 10, now we're going to talk about limiting reactants. And how we can understand limiting reactants is let's take the simple example first, where we have some carbon atoms reacting with oxygen, and that's just kind of depicted here. You mix the two together and you're going to get CO2 in this reaction, okay? So if we were doing this in the laboratory, as is depicted here in this picture, we have three carbon atoms reacting with two molecules of oxygen with this equation, all right? So let's imagine we're doing this in the laboratory, we're mixing these guys together. In this case, though, the reaction will stop when the two molecules of oxygen are used up. And we're gonna get CO2 molecules, like I said here, carbon dioxide, but we're also going to get a leftover carbon atom that didn't have any oxygen to react with. Okay, so this is our introduction to limiting reactants. Okay, in this case, the reaction stops once we run out of oxygen. Okay, and we have some leftover carbon that didn't react. So this is just kind of illustrating the same thing that I just said, where two carbon dioxide molecules are going to form and one carbon atom will remain unreacted. So again, we start with three carbon atoms, two oxygen molecules, and no carbon dioxide molecules. We're going to use two of the carbons, two of the oxygen molecules. We're going to get two CO2 molecules, but we're going to have one leftover carbon atom. Okay, so the limiting reactant is the reactant that is completely used up. In this case, okay, that's going to be O2 because we have no O2 left. And the excess reactant is the reactant initially present in excess, which is going to be carbon. Okay. So again, this is a simple example, and we're going to do some math, some stoichiometry to figure out this for harder problems. But this is just to give you an idea of what we mean by a limiting reactant. Okay, so here's how you're going to calculate a limiting reactant problem. We're going to be using the tools we learned in percent yield, and before that, mass-to-mass stoichiometry. That's really what we're going to be using. We want to be able to calculate the amount of a product formed by the initial amounts of each reactant, okay? And the reactant that yields a smaller amount of product is the limiting reactant, okay? And then the smaller amount of product is the amount that will be formed when all the limiting reactant is used up, okay? And we can calculate the amount of excess reactant, and we can subtract from the amount of excess reactant present initially, the amount that is used by all the limiting reactant, and the difference is the amount of excess reactant that is left over. We're not so much going to be focusing on those so far in this class. What we want to be able to do, or I should say in this video, but what we want to be able to do is just figure out which is the limiting reactant and how much of the product we form. So really the first part there. Okay, let's just do some examples here. We're going to just start out with a simple example of converting moles to moles here. So how many moles of potassium nitrate can be made from 7.94 moles of potassium chloride and 9.96 moles of nitric acid by the reaction given here? Okay, so I'm not going to have enough room to write all of our given and wanted steps, but that's the same from what we've used all the way back from dimensional analysis. So what you're going to do, basically, you're going to do two conversions. First, we're going to convert moles of potassium chloride to moles of potassium nitrate. And then we want to convert moles of nitric acid to moles of potassium nitrate. Okay. So let's just do that. I'm just going to write that out here. Okay. We're going to use our ratios of coefficients here, mole ratios. So we have 7.95 moles potassium chloride times, well, for every 3 moles of potassium chloride, there are 3 moles of potassium nitrate. Okay, so we're just going to get 7.94 moles here because the 3's cancel out. Oh, I'm sorry. That's the wrong compound there of potassium nitrate. Okay. So down here, let's do the same exact equation, or not equation, the same exact type of conversion, but now we're going to be starting with 9.96 moles of nitric acid. Okay, so from here, for every 4 moles of nitric acid, there are 3 moles of potassium nitrate. Again, just right from this equation. Okay, so when you put that in your calculator, I get 7.47 moles of potassium nitrate. And so for these limiting reactant problems, okay, this is a lower amount of moles of potassium nitrate. So it is kind of the cap on what I can form, like in the example with the carbon dioxide molecules and the leftover carbon. In this case, once my nitric acid is used up, which is my limiting reactant or reagent, okay, the reaction stops and I can only produce 7.47 moles of potassium nitrate, okay? So the rest is in excess. All right, so that's how we will answer problems like this, but let's kind of increase the difficulty. Let's try to convert mass to mass. All right, here's another problem. A 24-gram piece of solid sodium is added to a 24 grams of liquid water. How many grams of hydrogen are produced? Okay, so as with all of these equations, as we've seen so far, we need to be able to write out the chemical equations that are going on. So we have sodium, okay, solid. This is something we're going to see in a later video in chapter 9, okay, plus liquid water, okay. I'll write it like this for now. Gives me, so this is a single replacement reaction, which is the reason I wrote it like this. It's A and BX gives me B and AX, okay? So this is going to be B, hydrogen, which is diatomic, it's a gas, plus sodium hydroxide, aqueous, okay? And we need to balance this equation, and I believe we'll do that like so. Okay, so that's the reason I wrote water HOH instead of H2O. I think it helps you when you do that, okay? So now we have 2 sodiums on either side, 2 oxygens on either side, and 4 hydrogens on either side. Yes, so this is a balanced chemical equation. So that step is done. All right, now, again, we're gonna do 2 mass to mass conversions here. First, I'll just erase this for now so it's less messy. We're going to convert grams of sodium to grams of hydrogen. And then we're going to convert grams of water to grams of hydrogen. And we're going to see which one is lower, right? Which conversion gives us the lower number. And that's going to be our answer. Okay. So let's go through it together. So we'll start first. 24.0 grams of sodium, okay? I want to convert that to moles of sodium, right, from our mass to mass conversions. We're going to use the same exact template. Remember I mentioned that if you just memorize how you do these conversions, it's going to be a lot easier for you. So there's 2 moles of sodium now. This is coming from our chemical equation. For every 1 mole of H2, okay, there's a 1 there, times for every 1 mole H2, there are 2.02 grams of H2, I believe, okay? And when I put that all in my calculator, I get approximately 1.05 grams of hydrogen, okay? So that's that. So now we're going to do that conversion again. Now we're going to start with grams of water. Okay, and then as with our steps, we convert that to moles of water. Okay, it's about 18.02 grams of water, I think it is. Times your numbers might be slightly different than mine. That's okay. So 1 mole of H2 gives me, for every 2 moles of water. Okay, and then the same 2.02 grams of H2, 1 mole H2. Okay, and here I get 1.35 grams of H2. Okay, so what this is telling me is that when I put 24 grams of sodium and 24 grams of liquid water, I'm only going to get a maximum of 1.05 grams of hydrogen, okay? And once my sodium is used up, right, this is how much I can produce with that much sodium, okay? Then the reaction stops, okay? So sodium here is my limiting reagent or reactant, and I can only produce 1.05 grams of hydrogen, okay? You pick the lower amount again. All right, so why don't you pause the video and do this example? I'll give you a hint. It's a combination reaction, okay? And why don't you do this problem? Okay, so assuming you were able to do this problem okay, I hope you were. Let's write down the reaction. So we have antimony plus 3 iodides, or iodines, I should say, gives me this. Okay, so again, we're going to do 2 mass-to-mass stoichiometry problems. Okay, so 129 grams of antimony, we'll just start with this guy and convert it to grams of this compound here. So for every 1 mole of antimony, okay, there's 121.76 grams of antimony off the periodic table. And then the molar ratios here, for every 2 moles of this guy here, there's 2 moles of antimony here. And then times for every 1 mole here. If you got its molar mass by adding the masses of antimony and 3 iodide compounds, this is what you get, I believe. Okay, so you put all that in your calculator, and I get about 532 grams of this compound. Okay, so now you just do the same exact thing again. All right, so it's going to be so repetitive. You're going to do so many of these that, again, the pattern, I think, is just going to be stuck in your head, and they're going to become pretty easy, which is my hope for you, that they become pretty easy. Okay, 2, okay, 253.8 grams by 2. Okay, 3 moles this time of iodine because of the coefficient there. For 2 moles, this guy. Sorry, I have to write all this out. I'm just waiting to see if you got the same answer as me. Okay, so I put all that in my calculator. I get 503 grams of this compound. Okay, so that is my answer. That's how much I can form. All right, so that the iodine here limits the reaction going forward, and once I run out of it, the reaction stops, and I can only produce up to 503 grams of this compound. Okay, so you cannot produce 532. All right, so again, these are how you do those problems. You basically do mass-to-mass stoichiometry twice. You see which one gives you the lower mass of your product, and then that is the answer of how much you can produce, okay? And what is the limiting reagent, which is iodine in this case. Okay, so here's a final problem that we'll do together. Again, hopefully it's becoming a little bit repetitive, but this one is a little bit different, okay? So this is the reason I put it in there. So it says, now it's asking a slightly different question. Is 135 grams of sodium carbonate enough to neutralize a solution that contains 188 grams of nitric acid? Okay, so that's the first part of the question. And the second part is then, okay, once you figure that out, how many grams of carbon dioxide will be released in the reaction? All right, so how are we going to do this problem? Well, if we want to know how many grams of sodium carbonate are required to neutralize 188 grams of nitric acid, what we should do is convert grams of nitric acid to grams of sodium carbonate, right? Because there's some molar ratio between the two for however many moles of nitric acid that will react with a certain number of moles of sodium carbonate. And I know I can convert that to grams. So if I do a mass-to-mass stoichiometry problem of converting grams of nitric acid to grams of sodium carbonate, I'll be able to figure out exactly how many grams of sodium carbonate I need. And hopefully that makes sense because, again, there's this relationship from the chemical formula here, the balanced chemical equation, that tells me this ratio between the compounds here. All right. So let's do that. Let's, for the first part here, convert 188 grams of nitric acid to grams of sodium carbonate. Okay. So if you put all that in your calculator, this is what I get. Well, I guess if you write it all down, then we'll put it in our calculator. So this is nitric acid times for, let's see here, 63.02 grams of nitric acid, 1 mole. Okay, for every 2 moles nitric acid. Okay, from the balanced chemical equation, there's 1 mole of sodium carbonate. Okay, and then for every 1 mole of sodium carbonate, there are 105.99 grams of sodium carbonate. So when I put all that into my calculator, I got 158 grams of sodium carbonate. Okay? So that's my answer there. So then the question is, remember, if we go back, is 135 grams of sodium carbonate enough to neutralize a solution that contains 188 grams of nitric acid? And through this mass-to-mass stoichiometry, I would say no, right? The answer is no. Okay, to here, no, this is not right, okay? I need more material. I need at least 158 grams of sodium carbonate to neutralize this much nitric acid. Okay, so 135 grams. Okay, is not enough. Okay, so like I said, just a little bit of a variant on the problems that we've already been doing. Okay, so what about the second part then? Well, let me just erase everything that I have here, okay? And hopefully you have it written down. Can I just erase? And it's like, great. Okay, that's much quicker than I was doing in the last video. Okay, so how about this? How many grams of carbon dioxide will be released in the reaction? Well, we already know that I'm limited by the amount of sodium carbonate, right? Because I don't have enough to neutralize all the nitric acid. So once I run out of sodium carbonate, the reaction is going to stop. So what we need to do then is convert grams of sodium carbonate to grams of carbon dioxide. Okay, so let's do that. So I'll just erase here. Okay, so again, just give me a second to write all this down. 105.99 grams of sodium carbonate, 1 mole sodium carbonate. Okay. For every 1 mole of CO2, there's 1 mole of sodium carbonate from the balanced chemical reaction. And then for every about 44 grams, I think it's like 44.02 grams of CO2, there's 1 mole CO2. So I get there 56.04 grams CO2, okay, which is my answer. Now, let's say you don't believe me, all right? So this is how many grams of CO2 we can produce because sodium carbonate is our limiting reactant here. But let's say you didn't believe me. You could still convert grams of nitric acid to grams of carbon dioxide. Okay, so I'll just do that here. You don't need to do this based on what we did in the previous step, okay, answering the question here. But let's just do that. Okay. HNO3. Okay, and you get here 65.7 grams CO2. Okay, so again, this is not right, because we picked the smaller number here to figure out how much we can really produce, because once we run out of sodium carbonate, the reaction stops. Okay, so again, this is my real answer, but if you were just unsure, if you're in the homework or a quiz or a test and you just wanted to double check, just do a little bit of extra work and give yourself some peace of mind there. But the answer here is going to be 56.04 grams. Okay, and actually, if I wanted that with the proper number of significant figures, it'd just be 56.0. Okay, because I started out with 3 significant figures. All right, so hopefully the limiting reactants isn't too much trouble for you. That's it for this section, and I'll see you in the next videos.